Yeah, welcome to the last Compass Friday seminar in this academic year. We have a special guest today, Christine Gommenginger of the National Oceanography Center in Southampton. I have known her for about 25 years, I think, and it's very nice that she agreed to give this presentation for us today. Christine got a diploma degree, a kind of master's degree in electromagnetics, telecommunications, and remote sensing at the universities of Toulon and in Nice in France a long time ago. And then she went to Southampton and got a PhD in microwave radar remote sensing of the ocean at low grazing angles. That's what her CV says. So it's a very well defined, very specific PhD. So she has been in Southampton since the late 1990s. She is now a professor and a leader of the satellite oceanography group there. Her research interests include active and passive microwave remote sensing of the ocean, the understanding interactions of microwave signals with the ocean surface, remote sensing of ocean wind and waves, developing new Earth observation technologies and applications, wide swath ocean altimetry, altimetry for sea state, long track interferometry for current measurements, global navigation satellite system reflectometry, SAR altimetry, salinity measurements from space. So all these things. She has 60 publications, I think, as a first author or co-author, which is quite a lot, more than I have. And a fun fact about Christine is that when we started to work together in the late 1990s, we had a project that was called SEASTAR. And then about 10 years later, or a little more, I went to this place where John Hargrove is working as well, who just came online, which is called SEASTARS. And then another 10 years later, Christine submitted a proposal to ESA for a new satellite mission called SEASTAR. So this is a recurring theme, SEASTAR, in our careers, and we have always had some communications about these activities. I'm also a team member on this SEASTAR proposal, so I thought this is a perfect thing for our seminar. And so, Christine, go ahead and give your presentation on your SEASTAR satellite.
Thank you very much, Roland, and thank you very much for this invitation to speak to you all about this SEASTAR mission proposal, which I have submitted to ESA. Which I'll say a little bit more about in a minute. I'm going to try and share my screen so we can have some slides. So let's see if that works. Here you go. It worked earlier. So, question is, what do you see? Is that all right? Can you see my slide?
No, I see the presenter mode now.
Okay.
That was better 10 minutes ago. Yeah, now it's good.
Now it's good?
Yes.
Okay, perfect. So I will be talking about this satellite mission candidate that I have submitted to the European Space Agency to measure small-scale ocean surface dynamics and vertical ocean processes in coastal shelves and polar seas. Sorry, just working out how to run this. Roland, thank you very much for this introduction. I will go through this relatively quickly, really to highlight a bit of a disclaimer, if you like. So my main area of expertise is ocean remote sensing, and Roland has explained I have a very wide range of interests, from currents to winds, waves, sea level, salinity, etc. And so I'm involved in many missions and many different techniques. Really just to say, I do have a background in physical oceanography, so my interest in remote sensing is driven by answering questions linked to physical oceanography, including topics such as sea interactions, transport, circulation, increasingly coastal changes, extremes, and variability and trends on longer timescales, such as through the ESA Climate Change Initiative program, which I'm active in several projects. I'm also a promoter and a proposer of innovative Earth observation. Roland mentioned the GNSS reflectometry, which some of you will know from the NASA Cygnus mission, probably in the US to measure hurricane winds. And we have equivalent kind of missions in Europe, TechDemosat-1 in the UK. And then more recently, the ESA candidate Scout mission Hydro-GNSS, which has now been approved to go forward. But today I'm going to be talking to you about SEASTAR, this is the outline of the talk. First of all, I'm going to outline, to describe the science drivers, what has actually motivated the submission of this SEASTAR mission. Really to identify recent research that has driven that, what are the observational needs and the knowledge gaps that it seeks to complete. And then I'll give you some brief sort of description, some key elements of the SEASTAR mission and some of the key take-home messages, if you like, of the mission and what it consists of. The motivation for SEASTAR is very well encapsulated by this satellite image. This is a Sentinel-2 spectral optical image taken in the Baltic Sea in July 2019, showing this incredible range of variability at very small scales, at scales around 10 kilometers scales, as you can see. And we see these kind of fronts and filaments and swirls really quite frequently in ocean color, high resolution ocean color, and sometimes also sea surface temperature images. These are especially frequent near mesoscale jets and eddies in coastal seas, at the continental shelf break, and also close to sea ice margins. So we know that they are essentially fingerprints of real dynamic interactions between the atmosphere and the ocean occurring at those small scales, and also of vertical processes in the upper ocean, which is why we see the effect of these dynamics through the response by in this particular case, algae blooms. And it's fair to say that apart from those very nice images, there is actually relatively little information about the dynamics that are associated with these phenomena. There are obviously some in situ measurements of this, but it remains a very challenging type process to observe. And this is where satellite Earth observation has a particular strong role to play. And of course, these kind of phenomena are of great relevance both for science but also for society, because these vertical exchanges between the surface boundary layer and the ocean interior are very relevant from the point of view, for example, of nutrient supply at the surface that drive marine ecosystems, but also conversely about exchanges of heat and gases and indeed fresh water between the ocean surface and the ocean interior. It's also been shown that these phenomena, these small-scale dynamics, play a very important role in lateral dispersion and transport, and I will show a little bit more of this evidence later on. And clearly, from the evidence from the satellites, we know that these are quite strongly linked to what's happening in coastal seas with regards to interactions with land, but also in polar seas, interactions between the air, sea, and the sea ice. So ocean submesoscales, which is the sort of general word that is used in the ocean literature, has appeared in recent years, has been known for a long time, but has seen a resurgence of interest in recent years. Just to define, submesoscale typically are represented by scales shorter than 50 kilometers. And more recently, there have been more associated with scales below about 10 kilometers. Like I said, there's been a lot of more recent publications on this, starting first of all with very high impact publications on really the role of these dynamics on the marine ecosystems and the impact it has on the marine biogeochemistry, but also, as I said, this evidence of the role that they play in the dispersion and the redistribution of floating material like marine debris or oil and so on. And again, I'll mention this a bit later. And then more recently, as you can see, the dates from these publications are very, very recent. There are some coming out practically every week on this particular topic, really capturing the fact that these small scales have got impact on large scales and on sometimes some very unexpected effects in the climate system. And there are many, many more. So this is very much a very superficial kind of tour, but there are hundreds and hundreds of publications on this topic, and it's a very, very active area of research at the moment. And of course, you know, I'm sure you are all familiar with the SWOT mission, Surface Water and Ocean Topography mission, which is due to be launched sometime in 2022. And SWOT is very much has driven a lot of this interest in what dynamics at the smaller scales by proposing to take measurements of ocean surface topography at scales of around about 1 kilometer, specifically to complement or to address the limitations of present-day altimetry, nadir altimeters that cannot detect the variability of the ocean at scales below around about 70 kilometers at present. So SWOT, obviously, you know, this imminent mission, very, very large budget, very challenging mission, has attracted a lot of interest from the wider scientific community about this particular topic. So, like I said, the need for 1 kilometer resolution has received a lot of attention. And this is a lot of what we know about this comes from the numerical modeling world. In this particular instance, one of the very first numerical simulations of its type, where models were run at different resolutions to show really that the dynamics of the ocean change really quite dramatically as you reach scales around about 1 kilometer. And these models kind of, and the theory predict that there's a lot of enhanced coupling between the atmosphere and the ocean through interactions between wind, wave and currents at the interface. And it really highlights the importance of ageostrophic effects and interactions between those secondary ageostrophic phenomena and surface winds. With the result being enhanced mixing in the upper ocean, as well as enhanced vertical transport, which again has this impact on marine biogeochemistry. So a lot of this knowledge, or a lot of the interest in this has also been driven by what the models have been hypothesizing until now. Of course, a lot of this, very little of this has received validation because, again, as I have mentioned, it's very challenging to observe these phenomena with traditional ocean observing methods. They are observations, and there have been very extensive campaigns to try to look at this, but they are incredibly challenging and still relatively rare. The other aspect has been these model simulations that have been trying to run different resolution models over longer timescales. So in this particular example, we have this experiment by Levy and et al. Of an idealized North Atlantic Basin type domain being run for over 100 years at 3 different resolutions. And you can see already from the figure how after 100 years, the field look very, very different in terms of, in this particular case, vorticity. But the changes the impact of actually resolving those small scales is really very, very wide. And as you can see from those other plots that show the distribution of surface velocity, but also the mixed layer depth, there are fundamental changes to the ocean circulation with much more energetic vortices at the final resolution, but also intensified jets, relocation of gyres, a jet that is more eastward, more zonal than it is at the typical sort of 12-kilometer resolution that is used in models these days, and shifted southward by several degrees, with really major impact on the stratification and the mixed layer depth. And this has impact, of course, on basin scale circulation, on thermohaline circulation, on meridional heat transport, as I mentioned, mixed layer depth and biogeochemistry. So just showing that these small scales below sort of 10 kilometers really have a major impact at large scales and long time scales as well. This is seen also in this particular example of a 1/30th of a degree simulation that shows how these dependence between those surface phenomena, vortices and so on, relate to the vertical structure of the ocean, and how that relationship changes between winter and summer. And there is good evidence now of these seasonal changes, which are obviously very relevant because they will affect the way the ocean and the atmosphere interact in different seasons, depending on the structure of the underlying ocean. So I mentioned also already the key role of these small scales in lateral dispersion, and just want to bring to your attention, if you're not aware of this already, of some of these experiments that have been run with mass releases of surface drifters, which have revealed this very unknown until now patterns of convergence and clustering and dispersion associated with submesoscales. So most famously in this paper by D'Assauro et al, where these surface drifters have been kind of clustering and redispersing in very unexpected ways. This is very much one of the first time that this has been observed. And this is obviously directly relevant to any floating material and its dispersion, such as oil, plastics, or indeed sargassum in the Atlantic. And on the right-hand side, really an experiment also with surface drifters during the deep water horizon spill, and the conclusion there was that essentially they released some surface drifters in the vicinity of the spill and looked what happened at the drifters, and forecasted also using the models, but also satellite altimetry derived velocity fields. And they very much confirmed that both the models and the altimeter derived fields are just totally unable to capture the dispersion of this floating material. And really their conclusion was that there are still really fundamental questions about the structure of the velocity field at these submesoscales, which remain unresolved due to the lack of synoptic measurements at these scales. So these are some of the arguments that have kind of motivated our interest in this particular topic. Finally, last but not least, these submesoscale variability or phenomena is also seen quite frequently in satellite images of marginal ice zones. Here's a very nice examples in 3 different regions of the marginal ice zone, showing very clear patterns of eddies and swirls and so on, also in the sea ice, or the sea ice margins. And here things get even more complicated, of course, because in addition to all the other complexities of air-sea interactions, you also have the interactions with the sea ice, and in particular the differential wind stress over the water and the ice, and buoyancy gradients linked to heat fluxes and melting, and of course the mechanical action of the waves and the currents that change the ice rheology and the way it evolves in terms of freezing and melting. And again, here there is a really severe lack of synoptic observations of the sea ice dynamics that involve the full package that you need, which is really to know about the current vectors, the winds and the waves simultaneously. And the same goes for coastal and shelf seas. This is an example from, again, it's ocean color in just off Gibraltar, showing those patterns in this case sediment patterns from a river plume just off Cadiz. And coastal and shelf seas are obviously dominated by much more complex dynamics, also occurring, generally speaking, at small scales. Lots of geostrophic currents, lots of heterogeneity in the wind field, but also actually the wave field as well, because of the presence of the coast and the bathymetry. The relevance of this, I don't think I need to go too much into this, but obviously this coastal circulation is very relevant to a whole range of things, not least coastal erosion, pollution tracking and the like. And really our best understanding of what's happening in the coastal zone at the moment comes from high resolution models. And those models are still, what is happening in the coastal and shelf sea is still relatively poorly represented in the global models. And it is generally admitted that finer resolution of the order 1 kilometer and this coupling, better representation of coupling between the atmosphere, the wave field and the ocean is really going to be needed to advance this field in the next 10 years. So again, this all builds towards this case for new synoptic high resolution observation of currents, winds and waves, and to try to provide these type of observations in a more regular and more systematic ways to validate models and also approve parameterizations. So what do we actually know, having said all this, how much do we know about the magnitude, the occurrence, spatial and the seasonal distribution of these phenomena? Obviously, we have lots of satellite data. So we have many examples such as this one. We know that, for example, the high latitude is a very good place to go if you're interested in getting pretty pictures like this one. This is not a painting. This is a real image of Sentinel-2, again, optics. In Barents Sea in spring. So we know that spring bloom time, you're going to have some very nice examples like this. This is an example in the Barents Sea between Spain and Algeria, Morocco, very famous for all sorts of upwellings and complicated sort of eddies and so on in that particular area. This is chlorophyll. And this is, you can sometimes also, in this particular case, we had set sea surface temperature at the same time. And you recognize the sort of similar patterns between the two properties in this particular instance. This is not always the case, but in this particular instance, it was. So again, this is linked to upwelling, linked to the sort of large scale mesoscale variability, and that is all fine. But we see all sorts of other things. And here's a picture of the Gulf of Oman with some weird and wonderful features, which are very beautiful, but we have absolutely no idea of the dynamics associated with this. What is this associated with a very intense event or not is very difficult to say. And sometimes here, an example in the Adriatic, this has not necessarily anything to do with biology. Here it is much more likely to be a pattern picked up from the transport of some other suspended material in the water. So these are all very beautiful pictures, but really my word is of caution. Remember that these are hand-picked examples. It's actually incredibly difficult to find beautiful satellite images that are cloud-free and show those features. So it's a self-selecting sample of what these phenomena look like. We don't know what's happening in areas where the that are cloudy, for example. So we're very much looking for means of seeing through this to be able to get a more systematic understanding of the distributions and magnitude of these phenomena. As I said, more typically, these high-resolution optical and infrared images are impacted by clouds. So what are the science objectives of SEASTAR? Really based on what I have was just tried to explain. The primary objectives of SEASTAR are to measure for the first time the two-dimensional fields of total surface current vectors and wind vectors with a 1 kilometer resolution. The 2D field, because we're interested in the large-scale structure, the total surface current vectors, because we are interested not just in geostrophic currents, but in the total currents, in the wind vectors, because we're interested in this interaction between the surface currents and the winds, and the 1 kilometer resolution, because this is really the resolution you need if you want to be able to look at these. The key there is really this fine resolution, but also achieving this with high accuracy, because the magnitude of these phenomena can be quite low in some cases, and you would need good accuracy in order to be able to really detect or depict those structures with sufficient confidence. We want to do this over all coastal areas, shelf seas, and marginal ice zones, to characterize the magnitude, the spatial characteristics, the regional extent, the temporal variability on daily, seasonal, multi-annual timescales. This is what SEASTAR is aiming for. Daily is a real challenge, but these small scales decorrelate very, very quickly. So you do need to be able to provide both the wide swath capability, but also a relatively rapid revisit to be able to see how these structures actually evolve in time as well. These are sort of objectives that derive from the first one, and that is about delivering these higher order derivative products like vorticity and strain, divergence, really to look at the relationship between these phenomena and air sea fluxes and vertical processes in the upper ocean. And then finally, really to investigate the relationship between small-scale dynamics, air sea interactions, vertical processes, using a synergy of with high-resolution satellite from other sensors like optical, thermal, and other microwave sensors. And last but not least, to validate, providing those data to validate high resolution and coupled model and develop new parameterization to be able to represent these phenomena more appropriately in climate models in particular. There's a number of secondary objectives as well for SEASTAR. They relate mainly to the marginal ice zone and the coastal seas. The first one is about getting improved measurements of sea ice drift vectors instantaneously. So at the moment we only have sea ice drift in one direction, and they tend to be averaged over a number of days. Here we want to look at instantaneous fields really, and again with high accuracy to look at some of these interactions happening on shorter timescales. The other objectives are linked to new experimental products, linked to the capability of the SEASTAR instrument, and finally, something related to the river plumes, to look at the trajectory of, or look at the current and wind vector fields close to major estuaries to look at the dispersion of major river plumes. So the key elements of the SEASTAR mission concept is it's a microwave instrument, operates at a Ku band. So it's a synthetic aperture radar with a long track interferometric capability in several squinted azimuth direction. So that shows, the little figure shows the concept. You have essentially two synthetic aperture radars on the same platform that are separated in the along track direction by a certain distance that allows you to do comparisons of the phase measurement between the two snapshots of the same scenes. And by looking at the difference between those two, you actually get a measurement of the displacement of the surface in the time between the two snapshots. And here we're doing this in three directions. As you can see, we're looking squinted forwards by 45 degrees for squinting backwards, which the combination of these two will give you the current vector. And then we also look on the broadside to have a third look, which gives us the ability to also retrieve information about the wind vector. I will not dwell on this too much. I have already said a lot of that. The unique aspect of this mission really is to measure the total currents rather than just the geostrophic component or just the wind component. To measure the vector in a single pass, to provide high accuracy at 1 kilometer, to provide synoptic 2D maps of currents and wind fields. I haven't mentioned it so far, but these are synthetic aperture radars with high resolution images from which directional wave spectra can be derived. And really it's about delivering these simultaneous high resolution measurements of wind waves and current vectors over a relatively wide swath. Here we have a swath of 150 kilometers in the latest version of this concept. And we want to achieve this systematic mapping of currents and winds at 1 kilometer resolution in coastal, pole and shelf seas, as well as some open sites of special scientific interest. I'll say a bit more about this in a moment. Just a nod to Roland, who has worked on this years ago in the case of using a long track interferometry from the TandemX mission, for example. A long track interferometry is a very well-established technique. It dates back to the 80s, really. I have already said a lot of this really is about looking at the phase difference between two SAR images. And a long track interferometry essentially does that in 1D. SEASTAR will do this in 2 orthogonal directions from which you can retrieve the current vector. And the third look gives you the possibility to also retrieve the wind vector at the same time. I didn't mention, but we have polarization capability as well in the broadside direction, which gives us information about other smaller scale, even smaller scale processes like wave breaking and Langmuir circulation and things like that. Okay, so we have this concept has been around for a while. Actually, we used to be called WaveMill. It's now called SEASTAR because it seems I have a fixation about the word SEASTAR. So we have flown an airborne demonstrator of this concept several years, quite a while ago now, over the Irish Sea, and did some validation of these measurements against HF radar and high resolution model data. And the performance we obtained is very encouraging, with RMS errors of better than 0.1 meter per second for the currents and better than 10 degrees for direction. This has been confirmed more recently with numerical simulations that shows that the excellent performance really for current and wind retrieval. So here the plot shows the RMS error of currents in red and winds in blue across the swath. And you see that in both cases, certainly for current, the performance is better than 0.1 meter per second across the whole swath. So it's very, very encouraging results, confirming the very high sensitivity of this particular concept. We have a new airborne demonstration, which is shown here in the lab in that photograph. And you can see those antennas pairs sort of squinting forwards and backwards, which is called OSCAR, Ocean Surface Current something radar. It's an airborne demonstrator. It's waiting, it's ready to go. It's just waiting for its first flight. Ironically, we are kind of being held back by the need to find an aircraft that can actually accommodate it, with a radome in particular being a bit of a special case. So we've had some delays there, but we are hopeful that this will be flown sometime over the next few months. The challenges, this is we're working on this with our partners at Airbus in the UK, and this is a sort of artist impression, if you like, of what the system actually would look like. There isn't the squinting is now done electronically, so the satellites look remarkably simple. Actually, it's just a kind of big, long, elongated sort of javelin type structure. But as you can see, it is 15 meters long, which is pretty big for a satellite. It would be the largest structure of its kind ever flown in space if this gets selected. Admittedly, the technology is relatively simple and mature, and low risk. We have very good handle on how to control this, and with sufficient level of accuracy to be able to achieve the performance that we state. The key issue is it is big, and it has to fit within the very tight cost envelope of the ESA Explorer missions. And that was our problems before, and hopefully will not be a problem this time, but we never know. So we'll just await to see what the outcome of the ESA selection is. The other challenge is really about this trade-off between the orbit choice and the space-time sampling. So we have this aim of observing all coastal shelves and polar seas, which actually imposes a sun-synchronous orbit. We would have had to have a sun-synchronous orbit anyway because of the huge power requirements of this instrument. So we are in sun-synchronous orbit. Essentially, in order to achieve the space-time sampling we have defined in our scientific objectives, we've decided to go into a mode of having several orbital phases, essentially. So we have on the left what we call phase 1, which is the proposed at the moment is to have a sort of 6 months time when we have a limited number of tracks that are repeated on a daily basis, and on each day we can acquire, I think, up to 150 scenes, each something like 250 kilometers long across 150 kilometers. So you see these sort of snapshots along the coastlines over the areas of interest. And then after 6 months we would move into a sort of 35-day repeat type orbit, which gives you then the sort of sampling or the repeat visit that you see here on the right plot over the English Channel in this particular instance, where you get of the order of 6 or 7 kind of overpasses in some regions within any 35-day period. So really it's a combination of requirements in the first instance to look at this small scale, the short-term variability of these phenomena over many different conditions. And then in the second case, really to do a more systematic sampling over all of these regions over the period of the mission. Mission lifetime at the moment is expected to be 5 years nominally, with a sort of a 7-year as a goal. The timing of this, if it is selected, the launch would be around 2031, 32. You can see there, it's quite a long time between the call coming out and the mission being launched. This shows how it compares with some of the other missions which we know will be flying at the time. So obviously there's a lot of complementarity with the other satellites from the Sentinel series. So the microwave radars from the Sentinel-1 series, the optics from Sentinel-2, the optics and the sea surface temperature from Sentinel-3, and of course the altimetry, the high resolution altimetry that we get from SAR altimeters like Sentinel-6, for example. By 2032, we'll have a whole new generation of missions, hopefully Crystal, which is a sort of polar altimeter, cryosat follow-on, as it's not unofficially known as. SIMA, again, sort of radiometer for looking at polar regions. So a lot of new missions looking at polar regions. Unfortunately, SEASTAR will not come in time to overlap with SWOT. As you can see, SWOT, even if it's launched in 2022, will not last long enough nominally to wait for SEASTAR to be launched. But you never know, there may well be a SWOT follow-on one way or another. Who knows? The unknowns at the moment are things like harmony, which some of you may be aware of, that was selected from the previous call, the Earth Explorer 10 call, harmony, that has some aims also for ocean current monitoring by taking some observations over parts of the world. And of course, there's always unknowns such as stream, which is also been submitted to Earth Explorer 11, is also supposed to do global observations of currents, more in a sort of Doppler scatterometer type way. And of course, WACM, which I'm sure many of you will be familiar with in the US, also based on the Doppler scatterometer type concept. So there's a lot of interest at the moment in surface current missions. It's a crowded field. SEASTAR is one of many, and we'll see what happens in the next few years. But actually, we won't have to wait for a few years, but because certainly the decision for SEASTAR is imminent. With the review panel met this week, we're expecting to hear hopefully next week, or certainly in the next couple of weeks. And we remain optimistic. I think we have a strong case. But you never know with ESA, anything could happen. If we are selected, it's still a long way ahead. As I said, 2032 would be the launch, and there are several kind of steps in between where you can still fail. So if you're selected at this stage, there'll be a year of phase 0 for up to 4 candidates will be selected to go for these sort of feasibility studies for about a year. Then 2 of those candidates will be selected to go further into phase A. And then at the end of those 2 years, we go into a user consultation meeting, which is essentially a final shootout between the 2 candidates, and leading to final recommendation for one mission to go ahead. This is where having the support of the wide user community is really important, because this is where user consultation meeting is where the community can come and express support for one mission or the other. So it's incredibly important to raise awareness of those missions at an early stage to build in as much as possible the support of the community. In the meantime, if whatever happens, what we are doing at the moment is we continue to research this issue about how do we correct the wind wave biases that are present in SAR Doppler data in different sea conditions. Again, this is something that's not relevant just for SEASTAR, but also for Sentinel-1, for example, and indeed any SAR missions that are interested in measuring Doppler, taking Doppler observations. We are seeking opportunities to fly new airborne validation campaigns with the OSCAR instrument. And of course, we also want to plan more research studies using in situ airborne satellite and models to look at this relationship between small scale surface signatures, Earth interactions, and subsurface processes. And I think this is where I end. So thank you very much for your attention.
Okay, thank you very much for the nice presentation. And if people have questions, please do it like Lisa Biel and switch your camera on and your microphone and ask your question. Lisa, you had a question, or yes?
I had a question. Well,
Hi, Lisa.
Hey, Christine, how are you?
Okay.
This is really exciting for somebody who's interested in Western boundary currents.
Yes.
And I noticed that that you seem to have some missions, maybe in that first 6 months, some target places off of Africa, which is even more exciting to me. But you know, I had a couple of questions. I'm no expert in satellites, but my first question was not really very fair, because it was about SWAT. Why is that mission so short? And my second question is, you know, how come it takes so long to get this to get this online. You know, if you're lucky, let's hope you are, and get the okay from ESA. Why does it take 10 years to?
It's the processes of ESA are incredibly long and complicated. It is an issue. I mean, you know, sustaining the research interest and effort over 10 years is really difficult, you know, these days. But the ESA processes are still very, very long because there are multiple for each of those, you know, phase 0, phase A, etc. You have multiple teams being asked the same questions. So it's an incredibly rigorous kind of process with huge amount of administrative stuff and contracts with industry and so on. It's well-known problem, and I think people are trying to make it faster. The first question, I didn't understand your first question. I didn't grab what you said.
The first question was about SWOT. Why is the SWOT mission so short?
The SWOT mission so short? I don't know. You have to ask NASA, I think. Yes, and in fact, there's a huge, because I'm also on the SWOT science team, and there's a lot of discussion there about making, because SWOT is doing the same. They're starting with a 90-day, one-day repeat phase for CalBal, essentially. But the oceanographers really starting to get really interested in that also for the science, because, you know, doing those daily repeats will give us visibility of what's happening in terms of evolution of these short-scale processes that we haven't had until now. So a lot of oceanographers are saying, well, we could make it longer. Why don't we just make it longer? But no, the whole mission is 3.5 years maximum. And that has been made very, very clear. So I think it's linked to funding, I'm sure. Okay. Any other questions?
Tamay or Alex?
I can ask a question. Hi, Christine. This is
Hello.
very nice. I really enjoyed. Nice to meet you.
Nice to meet you.
So I was wondering, there is a lot of private effort, like Elon Musk and all these people throwing 400, 500 satellites. They are not, you know, research satellites. But do you see, like, especially considering the time frame that you have shown, you know, you are planning something for 2032, is there a way or method or somehow to link with these guys?
Well, if somebody can introduce me to him, that'd be great.
Yeah.
You know, I'll take all opportunities to make this happen. Definitely, yeah. I don't know to what extent that's a possibility, because these require the money is not enormous in the grand scheme of things compared to other things that are happening, but the size of the satellite is quite considerable, and I don't know if that may be a showstopper in this particular instance.
Because I see in the news, I mean, this guy is always throwing some stuff, some rockets, and then there's like 400 coming, 500 coming.
Yeah, they tend to be small, though. They tend to be small satellites. Large satellites are much harder work to launch. You need a lot more money. And
also, I have one more question. You seem to be really plugged in with all this. I never understood how NASA works with ESA. How does the whole thing? I mean, I see everybody kind of working together, US and Europe. Do you have a sense of this whole community? Roland is here.
So
I don't have a sense of the whole thing.
No, they are. So the space agencies do talk to each other. That, you know, it's one of those where they are in friendly competition, let's just say. You know, they like to collaborate, but they also like to be the first to do something. So but sometimes on some cases they are very, very happy to collaborate, and so at the moment I believe there are discussions going on about gravity missions, which may well end up being collaboration between US and ESA. these things are all possible. There's always a risk when you do a multilateral, as it's known, that one of the partners suddenly finds that they can't commit financially and the whole thing falls over, which unfortunately has happened to a number of missions in the past, not necessarily to do with the US, but with other partners. If one partner falls, for some reason hits a financial downturn for whatever reason, the whole project stalls. But certainly they are.
Asia, China.
So, yeah, it's all possible. It just needs a lot of work just to make it happen. You have to plan the idea and then follow it up, essentially. But yeah, if this is something you would be interested in investigating, it's something we can do a bilateral.
No, not really. I'm so far away from it. Roland is really our leading enhancer, of course. I noted it's the same name, SEASTAR. It's kind of funny.
Yeah, you missed
everything
the
I do
beginning.
is SEASTAR, apparently. I discovered.
I'm upset, but anyway.
I missed the beginning of the seminar where I explained that I met Christine in the late 90s when we had a project together with the name SEASTAR. And then 10 years later, I came to Miami to SEASTARS, and another 10 years later, she submitted this proposal for the SEASTARS satellite. If you watch the video this evening, you will see
I
how that
beginning. I
fits
was
together.
watching my story. Thank you. I really
Thank you. Thank you. Thanks for coming.
Thank you, Tamay. I think Alex Soloviev had another question.
Yeah, well, it's mostly comment. I was working on this near surface structure for years. And one of the conclusions was as soon as we see a strong near surface gradients or anything, then we see strong horizontal variability. It's almost linearly connected. And we observed this during Toga Core 1990s, and observed, of course, during Gulf of Mexico as part of CARS program, especially in 2017 when we had that leaking Taylor's platform that was perfect tracer for all these near surface structures. As soon as we get a wind speed below 5 meters per second, beautiful structures. As it goes above, they become more smooth or disappear at all. And that is because very strong dependence of near surface gradients on wind speed. It's like cubic of wind speed, and critical velocity is about 5 meters per second. If you go below 5 meters per second, everything becomes very different. And in this sense, I think very important that in your program you have planned to measure wind stress with high resolution. And also you have planned to do in situ measurements. Because when you look from space, satellite, and then you look in situ, sometimes you have very different conclusions.
And I didn't talk about this today, but the validation side of things is really challenging because we'll be measuring really just the motion of the surface. And in situ validation will be generally measuring in the top few centimeters at best, surface drifters, but even then they'll be measuring, in the top 20, 30 centimeters or deeper. And so then you have this issue, and that is a problem with many of the satellite observations, not just SEASTAR, is how do you actually validate what you see from the satellite compared to what you measure? Sea surface temperature is a typical one. But currents definitely is going to be an issue because of course we do expect big differences between the surface and the subsurface.
Also develop near surface jets, also under low wind speeds conditions. So that's actually a fantastic program. And 10 years after, we have much better opportunity to make measurements.
Well, in 10 years' time, this could be obsolete because, there may be, it is a real problem that it takes so long because the models are not waiting for this. They're just going full steam ahead. The models, even 1 kilometer resolution in 10 years' time may well not be sufficient.
Moon landing was in 1969.
Yes.
We didn't go forward, actually. We went backward.
Christine, do you think there's any opportunity? It sounds like this is way too big, but given the escalation in using drones for observing the surface ocean, and maybe the fact that that wouldn't take 10 years to get one in the in the air. Is there any opportunity for that with these kind of instruments or not?
The technology is not particularly good for small platforms. They're pretty hefty sort of instruments. You could go to a higher frequency to make them smaller, but the instrument would remain still relatively large. I mean, some drones are pretty good, some of the larger drones, but very quickly you end up with having to have an aircraft, something like this. But yeah, we're considering all this, certainly.
Yeah, but
can I just make a comment
for
Sure.
global measurement? I think we had Guillaume Novelli first. Did you have? Oh, you just switch your camera on to show your face.
Say hello.
Okay, then Lucy Wyatt, please.
Hi, Lucy.
Hi. I probably suggested this to you before in terms of validation, but the radar on the north coast of Cornwall, the University of Plymouth radar, would be a good site, because there they are able to measure waves, currents and winds out to 60 kilometres or so from the coast.
Yeah.
So it would be a good spot to aim at, I think.
Yeah. And in fact, actually, again, I didn't say anything about this today, because you also have to make the case for these missions in the context of everything, including HF radars and everything else. And very often I'm told, why bother with the coastal zone? We have HF radars. And it's true. And the network is growing. But there are still so many regions where there are no HF radars, and there is no prospect of getting HF radars for some time. So,
and also most of them don't measure waves and winds.
Indeed. So they're by far the closest, the best way for us to validate is actually going to be the HF radar systems. Yeah. So yeah, you need to talk to me, and we'll write a proposal to NOC, and we can do lots of great stuff.
Thank you.
Okay, thank
nice
you.
Talk.
Yeah, thank you.
Okay, do we have any further questions or comments? I don't see any. So
I have one more question.
Yes.
I think this economic depression that we are entering is going to affect since you're 2000, it's going to affect anything, or people are talking about in Europe or not?
So at the moment, yes, the economic depression is certainly going to have an impact, but it's not going to impact the size of these missions. What it might happen is that there are fewer calls for big missions. But there's a general recognition that even the budgets as they are at the moment are very, very tight for these very innovative missions. So it's very unlikely that those budgets are going to go down. Like I said, it's just that the calls will be less frequent. That's the way they're going to save that particular side of things, to try and make it happen. Because innovation, you can't. They are very reluctant to stop the innovation side of things, because that in itself kind of, it fuels all this sort of development of highly skilled jobs and economic growth and all that sort of stuff. So they see this as part of the solution, not
in Europe, that's the case, but not in US. In Europe, I know that a lot of people think like that. It's in the culture, but in US, science is the first thing that goes.
Well, in the US at the moment, you have many many things have changed very quickly recently. Obviously, change of administration is going to have a really big impact. But there's also, as you mentioned, this trend towards private sector space providers. And I think there's lots that the private sector can do, but there are also things that it will become very apparent they will not want to do. Difficult, risky things, possibly at some point, there may be a recognition that they will not want to do this. I don't know. I'm not, I can't read the future, but it's a bit the same in Europe. Can the private sector do this stuff and so on? And there is certainly some actors already making good competition really to those publicly funded satellites. But like, as always, private sector will only do certain things. They will not want to do everything, and certain things will not get done. Usually the challenging, risky stuff, like a mission like this, for example.
This reminded me of a question I wanted to ask. So when we submitted this, or when you submitted this initial SEASTAR proposal, that was Earth Explorer 10, right?
It was,
or I think we even considered Earth Explorer 9, and that somehow was too small, and then it was Earth Explorer 10.
That's right.
So now I didn't know that you are now in the race for Earth Explorer 11. Did they just
11. It came very somehow? Yeah, it was very quick. It came last year, a little bit out of the blue. The rules changed completely about who can be part of the proposing team and things like that. So in the end, I kind of spent most of my time talking to Airbus to trying to squeeze it into the funding, the financial envelope.
So you resubmitted it somehow as Explorer 11, and I'm not in the team anymore. That's why I didn't know about it. Or?
You're not in the team. You are, of course, you're in the team, but we were limited to 12 people.
Yeah, I see. Or maybe you even mentioned that somehow, but
we were limited to 12 people from Europe. Sorry.
Okay, very, very nice. I mean, that's really, really nice that it's again being considered. The last thing I remembered was that you were looking for potential other partners to make it happen.
I am, and I continue to, because for me, you know, the people you name on the proposal is such a small number of people compared to the interest there is in this. And I think the total list of people I have at the moment is over 70 people I have named who are interested in this. And my plan is always to retain that broader science team, because like I say, it's important to have a really large community supporting this, because the potential is very, very great. There's a lot to be done with a mission like this. There are many, many aspects, and you know, it's not possible for a dozen people is not going to be enough to exploit all the data, all the things that you could do, because of these multi-dimensions to do with submesoscale, coastal, polar, air-sea interactions, everything else. It's very, very broad topic.
Yeah, so, but when you have a smaller official team, you have more potential reviewers who can give you positive reviews.
Well, yes, that's actually the motivation by ESA was actually exactly that. Because the more people you have in the proposals, the smaller the pool of people to review it. But also because it's essentially, it prepares the grounds for the mission advisory board, and that has to be predominantly European kind of scientists from within ESA member states. I don't mean European, I mean ESA member states.
Yes, okay, I think that has been long enough. Thank you very much again for giving this really nice final presentation in our semester. I think this was one of the highlights of this academic year. And those who missed the beginning or who missed it altogether can watch it on YouTube at some later time, probably this evening. I will upload it. Thank you all for coming, and have a nice summer. I hope to see many of you again when we start the new season of Compass at the end of August.
Thank you very much for the invitation. Nice to see you all. Thank you.
Thank you, Chris.
Okay. Bye-bye.